Chapter 12, Introduction to Analysis of Variance, Part 3. In the previous video, I introduced the basic structure of our F statistic to conduct analysis of variance. And the basic structure is shown here. F is equal to the variance between treatments over the variance within treatments. And we learned that the sources of variance or difference in scores when we're looking at variations between treatments is attributed to treatment effect plus random unsystematic factors. And the variance within treatments, that variation of scores within each treatment condition is attributed to random unsystematic factors. Again, the difference between analysis of variance and a t-test is that the analysis of variance is focusing on the variation of scores and trying to assess whether that variation in scores is due to treatment or due to random unsystematic factors only. And the t-test focused on looking at the mean difference. So again, when we have more than two groups that we want to compare, more than two conditions, we cannot produce the mean difference, or calculate, I should say, the mean difference between three or more groups. So we also talked about this idea that if the treatment effects was equal to 0, and we add that to the random unsystematic factors, and then that over just the random unsystematic factors. Again, if our treatment effect is equal to 0, then our F value will be equal to or near 1.0. And again, we learned that the F distribution is positively skewed, and 1.0, F equal to 1.0 is representative of the null hypothesis, and the null briefly says that mu1 is equal to mu2 and mu2 is equal to mu3. In other words, we see no difference across conditions, that the average scores produced by these samples that are representative of populations would all equal one another. And so again, if we produce something equal to 1 or near 1, then we're providing support for the null hypothesis. However, if we find a value that's very far from 1, and in the positive tail, in the tail to the right, then we have support for the alternative hypothesis that says that at least one treatment condition is significantly different. So if I just put numbers to this and first say that if our treatment effect is equal to 0, and let's say we just produced random unsystematic factors equal to 2, and that's the same in our denominator, then we'd have 2 divided by 2, and that's equal to 1. Again, the null says no difference, right? No treatment effect. And if we produce an F value equal to 1, we have support for the null hypothesis. We would fail to reject the null hypothesis. Let's say instead our treatment effect is equal to 10. And again, please note, I'm just making up these numbers for you to see mathematically what we mean by an F ratio equal to or near 1. So now if we have a treatment effect equal to 10 added to the unsystematic factors of 2, we have 12 divided by 2, and we get an F ratio equal to 6. And that would be placed somewhere out here in the tail. Again, we're going to need an F, a critical F, to draw our conclusions about the null to determine if we get to reject it or fail to reject. That's going to be based on a critical F that we'll learn how to identify later in another video. So again, the F ratio is composed of two variances: variance between treatments over variance within treatments. Each of the two variances in the F ratio is calculated using the basic formula we learned in Chapter 4. So sample variance we learned was equal to S squared and that was equal to the sum of squared deviations over degrees of freedom. So again, when we talk about variance, you should recognize that this is the basic equation for computing variance. It's going to be a sum of squared deviations over degrees of freedom. And I'd like to introduce another variable used in this chapter when we can engage in analysis of variance. For this particular textbook, they use the variable ms, which represents mean squared, but that's equal to variance, or interchangeable with the concept of variance, which again is equal to s squared, which I just indicated is equal to ss over degrees of freedom. So again, don't be confused by this new variable ms. It's just means mean squared, and it's equivalent to the concept of variance. So they're just introducing a new variable to represent variance when we're talking about analysis of variance. So our F ratio will boil down to this equation, ms between, again, ms is the same as variance, variance between, which we see here, over ms within, right, which is the same as saying variance within. And we'll learn that ms between is calculated by taking ss between over its corresponding degrees of freedom. And then ms within is equal to ss within over its corresponding degrees of freedom. So again, this is our numerator, this is our denominator, and so what we need to do is compute SS values and identify degrees of freedom values for the variance between treatments, and then also for the variance within treatments. To obtain these SS and DF values, we must go through two separate analyses. First, we're going to compute the SS for the total study. Again, remember, SS represents a sum of squared deviations. So if it indicates that we have to compute or identify SS for the total, that pertains to the scores across all conditions. And then we're going to analyze this variable of SS total in two components, the between and the within. Then we'll compute DF for the total study and analyze it in two components, the between and the within. The entire process of ANOVA, analysis of variance, requires 9 separate calculations. 3 values for SS, 3 values for DF, 2 variances between and within, and a final F ratio. But before you allow your eyes to roll back in your head and develop math anxiety, know that all of these variables are very logically related to one another. And the next slide will hopefully see how they're connected with one another and help us simplify the process in computing the ultimate statistic, which is the F ratio. So before I present the equations for all these new variables, I want to review what I just presented, which is the final goal is to produce our F ratio. And I discussed that F is equal to variance between treatments over the variance within. And then I broke down that concept of variance, into 2 different components, the between and the within, which we see here and here. And now we recognize that these 2 values of SS between and with SS within contribute to this other third value, which we refer to SS total. So SS total, the sum of squared deviations across conditions, is equal to our SS between. Again, the equations will be presented very shortly, added to our SS within. So again, this value means that we take these two and take the summation to produce our SS total. And this is important because the equation for computing SS total is pretty straightforward, as is the SS within. The SS between is a little more complex and very time consuming. So we can understand, once we understand this relationship, if we want to produce SS between, then we know that all we need to do is calculate our SS total and subtract SS within. Similarly, if we started with SS within, which is a fairly easy and straightforward equation or calculation, we can determine the other variables, right? So if we have SS within, we compute SS total, and what's left, once we take total minus within, will give us the between. So similarly, if we want to solve for SS within, we would take SS total and minus SS between. So this is very important to have in your notes to save you that time, because again, the calculations for SS between is more complex and very time consuming. So we can save ourselves a lot of time simply by using this process. Again, relying on how these are logically related to one another. So similarly, for degrees of freedom total is degrees of freedom between added to degrees of freedom within. Again, the calculations will be presented shortly. So degrees of freedom total is equal to degrees of freedom between added to degrees of freedom within. So logically, we could compute degrees of freedom between by taking degrees of freedom total and subtracting degrees of freedom within. Or if we want to calculate degrees of freedom within, we can take degrees of freedom total and subtract degrees of freedom between. So again, it's important to have this in your these equations in your notes. Once we recognize the relationship, then we can use two variables to calculate the third without using the more extended variables that will be presented now. Actually, before I present the equations, let me introduce some of the new notation for the formulas. So number of treatment conditions is referred to as K. So if we go back to the example of the 3 telephone conditions in relation to driving performance, we had 3 different treatment conditions. So in that case, K would equal 3. So K is representative of how many conditions you're testing. The number of scores in each treatment is the same as we have learned since chapter 1. Sample size. So N sub 1 would denote sample size for a first condition. N sub 2 would indicate the sample size for a second condition. In chapter 1, we learned that capital N is representative of the population size. For analysis of variance, capital N represents the sum of sample sizes across conditions. So it's the total number of scores given all the conditions that we're testing. If the sample sizes are equal, for example, if sample size 1 is equal to 10, sample size 2 is equal to 10, and sample size 3 is equal to 10, then N would be the sum of all of these, so it would equal 30. But if they're all equal to one another, we could also calculate N by simply taking N and multiplying it by our K. So in this example, N is equal to 10 multiplied by 3, and that gives us 30. However, this equation of N, capital N is equal to lowercase n multiplied by K is only applicable if the sample sizes are equal. So it's not always useful. Instead, you would just take this total number of scores across conditions in instances where sample sizes are not equal. As we learned in chapter 3, the sum of x, we learned that when we calculated the mean of a sample, right? We took the sum of x over n. For analysis of variance, we're replacing sum of x with t. So if we're calculating the mean of something, we could simplify it and say it's t over n. Again, t is representative of the sum of scores for each treatment condition. The grand total of all scores, so again, the sum of scores across all conditions, is now referred to as G. And if we want to simplify that, it's simply taking the sum of all our t values, again, recognizing that t represents the sum of x for each condition. So if we want the sum of x across all conditions, that would be denoted by this capital G variable. And we should recognize that there is no universally accepted notation for the process of analysis of variance. In some other textbooks or other sources, you may see other symbols, but as long as you understand what each of these variables represents, you can interchange other notation that you may come across in subsequent statistics courses. So before we go any further, let's just first make sure we understand these new variables or the notation that was just presented. So table 12.1 shows the data for the test of different telephone conditions in relation to driving performance. So we have 3 different telephone treatments: no phone, handheld phone, and hands-free phone. And we learned that K represents how many treatment conditions we have. So again, we have 1, 2, 3 conditions. So that's where the K comes from. K is equal to 3. We just learned that lowercase n represents how many individuals in each condition. So we have 1, 2, 3, 4, 5. So our sample size is 5, and that's equal for all 3. So we have n sub 1 is equal to 5, n sub 2 is equal to 5, and n sub 3 is equal to 5. Capital N represents the total number of participants or scores that we have across all conditions. So again, in this case, all our sample sizes are equal. So we could say n is equal to lowercase n multiplied by k, and in this case that would equal 5 times 3, and that's where we get the 15. But again, if they weren't equal, we would just take the sum of these 3 values, right? It's the sum of all of the scores, or how many scores we have across conditions. We learned that T represents the sum of X. So before I discuss that, remember that sample mean is equal to the sum of X over N. So if we take the sum of X for this first condition, if we take the sum of all those scores, that's equal to 20. And we have 5 scores, so our mean for our first condition is equal to 4. So again, T now represents the sum of X for each individual condition. So again, sum of X, so we could replace that in that equation. Sum of X over N is the same as saying T over N, and that was still equal to 20 over 5, and we get our mean equal to 4. All right, and our G, right, is the sum of T. And so G represents the sum of X across conditions. So T just represents the sum of X for these 5 scores, but G represents the sum of that first set of scores plus the sum of the second set of scores plus the sum of our third set of scores. So it's the sum of X across conditions. And before I discuss this variable here, let's go back to the sum of square deviations and how we calculated or learn how to calculate that in chapter 4. So I'm going to erase all of this to free up some room. So in chapter 4, we learned that the sum of square deviations using our computational formula is equal to the sum of x squared minus the sum of x squared over n. So let's see how they calculated this value here. Let's replace the variables we know. So SS is equal to the sum of x is the same as t. So 20 squared over n, which is equal to 5. And the variable that's missing is this, the sum of all x values that have been squared. So let's quickly do that. 16, 9, 36, 3, and 16. So if we take the sum of these x values that have been squared, you should get 86. So SS for our first distribution is computed by taking 20 squared divided by 5 and subtracted from 86. And we should get that's equal to 6. So that's where the sum of square deviations for our first distribution value came from. Now this value over here is representative of and is often expressed as total. So you'll see this subnotation, meaning that it's the sum of all x values that have been squared across all conditions. So that means we would have to square this, right, this set of scores, as well as this last set of scores. We'd have to square all of these. And this value of 106 is the sum of all of these x values that have been squared, these values that have been squared, and these values that have been squared. So it's the sum of these three sets of scores. And again, you'll see it denoted often as total, so that it's not confused with just this value that's specific to one treatment condition. So hopefully this helps you better understand the new notation. And now we're going to look at the equations of how to compute the SS between and the SS within. So here are ANOVA equations. As indicated previously, we're going to begin and compute the SS for the total study and analyze it in two components, the between and within. So SS total is equal to the sum of x values that have been squared. Again, this is the x values that have been squared across all conditions. So this is equal to what I just reviewed given those three different conditions. We took all the x values in each condition, squared them, and then took the summation of all those x values that have been squared. And G, we learned, G is equal to the sum of t, so essentially we're taking the sum of x across all conditions and squaring that value. And then again, N represents the total number of scores we have across all conditions. So the word total is important to focus on because it's taking into account all of the x values, how many there are, what their values are, and considering them all together as one lump sum. The SS within treatment is equal to the sum of SS across conditions. So let's go back to that previous table. So I had shown you how we computed SS sub 1, so the sum of square deviations for our first distribution. So now we just learned that SS within is equal to the sum of SS. So in other words, we're taking all of these values. We compute the separate SS for each condition, and then SS within is equal to the sum of the SS across conditions. And this will be the easiest calculation simply because we're quite accustomed to calculating SS for different treatments, and now it's just the computation of the sum of all those SS to produce the SS within variable. So again, the within SS within treatments is simply saying take SS1 and add SS2 and add that to SS3. So the summation will give you SS within. And in all honesty, the SS between is the most complex calculation. And it's not very difficult, but it is time consuming because this part of the equation is represented by simply taking t sub 1 squared over n sub 1 adding it to t sub 2 squared over n sub 2 and t sub 3 squared over n3. So if you can imagine having more than 3 treatment conditions, this becomes quite complex. And again, the math isn't difficult, but it's time consuming. And again, don't lose sight of the fact that t is simply the sum of x within each treatment. So t is equal to sum of x within each treatment. But nonetheless, it's important to use this equation initially so that you can check your answers, because again, we have learned that SS total is SS within added to SS between. So if we begin with SS total and we calculate SS within, we can compute what SS between is without using this equation by simply taking, so again, I had indicated SS between can be computed by taking SS total and subtracting SS within, which is a much easier process. Nonetheless, we should know and learn this equation for no other reason than to check or reconcile our answer and recognize that either if we use this equation or this more simplified process, we should get the same answer for SS between. So figure 12.5 again helps us understand how these variables are related. So I just broke down how to compute SS total, and we recognize that SS total is the summation of our SS between added to our SS within. And that's helpful again for instances where we don't want to use this equation. We can simply take our SS total and subtract our SS within, which is a very easy calculation. And what will be left is our SS between treatments. So next, what we need to consider is the degrees of freedom for our different SS values. So the degrees of freedom equations, degrees of freedom total is equal to n, which is the total number of scores that we have across all conditions, minus 1. Degrees of freedom within is equal to the total number of scores we have, which is capital N minus K, and again, K is the number of treatments, right? Number of conditions. And N represents the total number of scores we have across all conditions. And the DF between is equal to number of conditions minus 1. So once we have degrees of freedom for these 3 different values, now we can compute our variance between and our variance within, because again, our MS between is equal to SS between over degrees of freedom between, and our MS within is equal to SS within over degrees of freedom within. So again, we just broke these 2 equations down, and we're introduced to the equations of how to compute SS between, SS within, and here we see the equations for degrees of freedom. And let's not lose sight of the ultimate goal is our F ratio, which is S at MS between over MS within. And figure 12.6 shows again the logical relationship between the degrees of freedom total and degrees of freedom between and degrees of freedom within. So the total is equal to the sum of these 2. Therefore, if you have degrees of freedom total and degrees of freedom within, you can then compute what degrees of freedom between is equal to. So again, understand the relationship between these variables to simplify things and simplify the equations. To summarize, here's a slide to present what I had initially started this video with simply presenting this concept of mean squared, which is the same as same variance. So we say variance between, or MS between, is equal to S squared, which is variance between, and we know that anytime we're computing the variance, it's SS divided by corresponding degrees of freedom. So again, this is reviewing what we just presented or went through step by step. And our F ratio, again, is MS between over MS within, which is simply saying the variance between over the variance within. So that's what we started with. We said F is equal to the variance between over the variance within. And this is the equation that we will use when we engage in the analysis of variance. Here is a ANOVA summary table. It presents information in a very concise presentation. It helps organize and direct the analysis of process. It's convenient for checking computations, and it's considered a standard statistical analysis program output. So once we use the calculations or equations that were just presented, and again, I will walk you through an example. Once we produce our statistics, so again, this value of 40 represents SS between, this represents DF between, and so we said that MS between, our equation is our SS between over DF between. So if we replace variables using this table, we show that SS between is equal to 40, DF between is equal to 2, so our MS between is equal to 20, and that's where this is coming from. Similarly, if we look at the within treatment SS values, or in particular calculation for MS within, the process is similar. So MS within, we learned, is equal to SS within over DF within. So SS within is equal to 20. DF within is equal to 10. So 20 divided by 10 gives us 2. So we see where this value is coming from. And then finally, we learned that F is equal to MS between over MS within, and MS between is equal to 20, MS within equal to 2. So our F statistic for this particular example is equal to 10, which again, given what we started with, the null represented by 1.00, a ratio 1.00 says that mu1 is equal to mu2, which is equal to mu3, meaning that there's no treatment effect. In F statistic of 10, right, it would put us way out into the tail, but again, we would need a critical F to draw the final conclusion, which we'll learn how to do in the next video. So we'll end this video with a learning check. Given what we just saw in that previous table and the relationship between variables, analysis of variance produces SS total equal to 80 and SS within equal to 30. For this analysis, what is SS between equal to? So again, SS total is equal to SS between plus SS within. So let's replace variables. We're told that SS total is equal to 80. SS between is what we want to figure out. And SS within is equal to 30. So if we use basic algebra, move variables around, again, we want to calculate SS between or solve for SS between. So then that would mean we would take 80 and subtract 30, and so our SS between is equal to 50. And you probably didn't need all of those steps to figure out what SS between is equal to, but here you see it logically presented, and again, affirming the relationship between these variables. And that concludes the lecture for part 3 of chapter 12.